Now, I live for computational models. My work is all about numbers and equations. Low order, simple line, high order, a polynomial. Thank you very much. Well, that's getting started. My father is a teacher. He taught machining in a public school system. Now, of course, he also taught his children about tools, the selection of tools being one such thing. Now, my brothers and I are all engineers, so our tools are different from his tools, but his advice is still valid nonetheless. If I had a hammer, I'd hammer in the morning. Join me. I'd hammer in the evening all over this land. Excellent. Great song. What on earth does it mean? Should we use our hammer for every job, just randomly pounding on everything we see? To a man with a hammer, every problem looks like a nail. Just because you have a hammer does not mean you must use it. Thank you. It was a cheap shot. I had to take it. As naval architects and engineers, the design spiral drives us. So when we talk about tools, sometimes we talk about CAD tools or computational tools. And the design spiral gives us some advice as to which tools we want to use, from higher precision or lower precision, depending on the maturity of the product. I'd like you to consider this. 50% of a product's life cycle costs are determined by the results of the project's first 5%. When is the really important work done? My contention and what I would like to share with you is that early stage design is incredibly important. And this, by the time of the first design review, performance, cost, and schedule will have been determined to the first order, because the critical assumptions and choices will have been made. The really serious mistakes occur on the first day. They lock you into things that's going to stay with you the entire design. Now, successful model selection, we have to look at the proper models we're going to use, whether they're CAD models or computational models or physical models. We need to find models that hit that sweet spot, I call it, between facility and function, or precision. Now, CAD models, what's the purpose of the model? Is it to build an engine? This is a CAD model with over 64,000 individual surfaces. As we go to a lower order or less precise tool, we actually may have models that are far better for the purposes at hand, and this is a great illustration of that. Now, I live for computational models. My work is all about numbers and equations. Low order, simple line, high order, a polynomial. Which is better? Who likes high precision? Who likes low precision? Oh, you're all so cowardly. Pick one. Are you sure? You can only be sure when it's put into the context of the project. Again, which is better? We have some simple points with different orders of tools or models. We have a simple line, we have a quadratic, and we have a cubic polynomial. We really don't know which is better until we understand the nature of things. Now, early in my career, I had a project doing weight estimating for fishing vessels, and they used a bounding volume called the cubic number. Now, that wasn't a very good model for weights because weights are a surface function. And so we actually needed a slightly higher order, the surface of that volume. Later on, I had a boss who insisted on doing material pickoffs for weights, even in the earliest stages of design. This was where too much order was a problem, because we didn't even have the geometry of the vessel established at that point. Hydrodynamic computational models. This is the world in which I live. The data model represents the hole in the water. The prediction models forecast performance, whether that's for hulls or propulsors. The order, I'll use bounding, parameters, volume, surface. And we'll see illustrations of that here in just a moment. Now, a bounding computational model is very, very simple. What is reasonable precision, however? These are two physical examples. This is model tests against full-scale resistance, and these are the best of the computational flow codes for propellers. There's such scatter in the data that anything better than 5% is an optimistic outcome. Now, the earliest resistance predictions are simple charts. We may recognize this as the Harvald chart. But how many ships can we fit into a common bounding box? Virtually an infinite number. This may be too low of an order for any meaningful work. If we take that bounding box and refine it a little bit into parameters, we can define the shape. We have to narrow the scope of the tool, however, because now we don't have a single tool that's useful for all things. We have tanker tools, we have fishing vessel tools, we have planing hull tools. Now, as we go into a higher order, we'll take this distribution and we'll identify its submerged volume. And we can use wave-making theory as an example of this to get very, very good predictions with a limited amount of data. This is kind of that middle order. Now, when we want to go to the highest order, we have problems that we can only use high-order tools. CFD is the perfect example of that, where we use the surface panels that describe the geometry. So why don't we always use the highest order tools? Well, they tend to be complex, they require calibration and correlation with empirical data sometimes, but the biggest problem is that we often get different outcomes. You take the same tool and give it to different people, and you get different answers. I love this quote: all models are wrong, but some are useful. If you take anything away today, take that away. The design spiral will help guide us to what models we do have that are going to be useful for our task at hand. All tools have a place, from napkin sketches to that CAD of 64,000, even hammers have a place in the 1990s. Thank you.